This demonstration using a Ladybug LB488 power sensor and a Berkeley Nucleonics Model 865 source, I'm going to show you how to make high sensitivity pulse measurements. I'm using external triggering, and there's 60 dB of attenuation between the source and the sensor. Okay, let's take a look at how you can use averaging and some other techniques to make a high sensitivity, high dynamic range pulse measurement. Now I've already showed you I've got 60 dB of attenuation between my sensor and my source. And I did that just to push the power down to where so that I can make this demonstration. My source is here. It's set for 5 gigahertz. My sensor is also set for 5 gigahertz. My power of my source, which is the pulse stop power, is 0 dBm. And let's take a look at the pulse that I've got set up. I've got a 100 microsecond repetition rate and a 1 microsecond pulse rate. That's 0.001 milliseconds and 0.010 milliseconds in the repetition time. And let's jump over to the power meter here. So I've got averaging turned off, and the pulse is there, but you can't see it. The reason for that is it's buried in the noise. The sensor is set to trigger on the pulse internally. It's set for auto level. I could try to set it to manual level, but it won't pick it up because the noise is jumping up higher than the power level is, and the sensor doesn't know what to trigger on. So now I'm going to set that to external TTL, and as you saw, I have a cable connected to the source's trigger output, and I'll be able to trigger on the pulse, and so it will show up as a pulse once it's pulled out by its triggering. So there are my pulses. I've got 2 of them on the screen. If I want to change that, I can go to the main display and change the sweep time, but I don't really want to mess with that, but that's how you would accomplish that. Now I can also zoom in on this pulse, which I am going to do because I'll go down here in the bottom and make a couple of measurements in a second, but I can zoom in on any portion of the windows with this power meter. So now the signal is there, but you still can't do much with it. So we're going to turn on some averaging. So I'll put 10 averages in effect here. I'll set it so that I can click the button to manually reset them. Now it takes a little bit of time to make 10 averages on a trace display like this. Normally this sensor will make about 2,000 average measurements per second, but here we're making traces. And these traces are long, so there's many points to be averaged to average a trace out to get the noise out of the trace. And so there it's getting pretty clean. In fact, I could probably measure it now, but rather than do that, I'm going to change my averaging to 100, and you'll see that it'll start to clean up even more, but it will take it quite a few seconds to clean up. And while it's in the process of doing that, I'm going to show you some other features that we have here. I'm going to enable a marker, and it's just going to be a normal marker. It's marker 1 down here, and I'm going to set that at the top of the pulse there, and you see that it's showing its measurement point as minus 59 point some odd dBm, and we would expect to see a minus 60. Now I do have an offset in which it doesn't show right now, but I've got that in because I checked my attenuators. My attenuators back to back are off a little bit, so that offset is in there. I can also now put in a gate. So I'm going to put a gate A. I'm going to set that to be an average power gate. And I'm going to put that across the top of my pulse. And what that's going to do is that's going to average the points across the top of that pulse and giving me a more accuracy on what the pulse top power is, 59.62 or 63 dBm. And I'm going to turn on another a gate, another average power gate here, just so we can see what the off power is, and minus 67 dBm. There's that. Now there's another way we can filter this even more using the video filters, which I can turn on a video filter. I'm going to turn on a 1 megahertz filter. Now it's going to mess up our waveform a little bit, because it's And in fact, let me turn the averaging down to 10 so you can see that more quickly. And the reason it's done that is because the rise time of the pulse is being filtered out by this filter. So I can still use a filter. I'm just going to step it up to 5 megahertz, and I'll get a better rendition of my pulse there, and I can make a nice measurement. If I turn my averages back up to 100, you'll see that that this is a pretty clean signal here. And because the sensor has such a great dynamic range, and you can see we're down really low with this power measurement. You can't make this kind of a measurement with most power sensors. If you take one of our competitors' sensors they advertise as pulse sensors, these sensors are up around minus 35 dBm with their lower power levels, maybe minus 40. So this is a really powerful sensor for these kinds of high dynamic range measurements. Now I've said high dynamic range, but here we're doing high sensitivity. But this sensor will do a pulse just like this from minus 60 to plus 20. So it's quite a nice sensor, and here you can see how averaging can really clean up a signal. Averaging works this way on an average power measurement too. It works because your signal is consistent and noise is random. And when you start averaging those random numbers together, eventually they'll average into some number which is close to your noise floor, and which is this number down here on the B gate. It's essentially the noise floor of the sensor, not just the sensor, but the noise that may be coming out of the source as well. But that's how averaging can help you make a high dynamic range measurement. Thanks for watching.